All right, let's just jump right into this explainer. Today, we're exploring something you probably walk past every single day without noticing: how the modern built environment uses invisible, layered defenses to protect us from microscopic threats. It's kind of like a secret engineering war going on right under our noses, keeping us safe in the places we live, work, and commute. To break this down, we're going to use a defense in depth framework. We'll quickly cover 5 areas: the invisible daily threat, how antimicrobial copper works, proof in real world spaces, securing our drinking water, and finally, designing a safer future. Okay, part one, the invisible daily threat. Basically, the surfaces we touch and the water we drink. So, how long do deadly pathogens actually survive on the stuff we touch every single day? It's definitely a question we've all been forced to ask ourselves recently, especially when we're navigating highly crowded public transit or, say, healthcare facilities. Well, look at this. The contrast here is just staggering. On one hand, you've got viruses like SARS-CoV-2 lingering for days or literally even weeks on standard stainless steel or plastics. But then look at antimicrobial copper. It permanently neutralizes them in just a few hours. I mean, that is a massive, game-changing difference in how our physical spaces either harbor or destroy threats. Which brings us to section 2, how antimicrobial copper actually works, the microscopic battle. Picture this. Imagine a harmful bacterium just resting there on a normal, inert material like plastic. That pathogen is completely unaffected. It's perfectly intact and just, patiently waiting to hitch a ride on the next person who touches it. But put that same bug on copper, and man, it is a completely different story. The moment it makes contact, the cell membrane is weakened through massive lipid peroxidation. Basically, think of it like rapidly rusting the cell's armor. This lets copper ions physically breach the cell, choke off its respiration, and completely scramble the bacteria's DNA. It literally destroys the threat from the inside out. And this microscopic destruction is absolutely vital. Why? Because nosocomial or healthcare-acquired infections cause up to 100,000 deaths a year in the EU alone. That's a huge number. So the materials we choose to build our hospitals with, they play a massive role in this fight. The hard data on this is honestly stunning. Researchers at the Institute of Virology at the University of Pisa found that the viral load of SARS-CoV-2 on copper is completely 100% neutralized in just 60 minutes. It's a permanent germ-killing effect, and it's driven entirely by the natural, intrinsic properties of the metal itself. No batteries required. If you take a close look at this data, you'll see the drop in viral load is incredibly rapid and logarithmic. Check out the pure copper column. There's over a 90% reduction in just 10 short minutes. It's continuously sanitizing itself, around the clock, without needing any chemical sprays, wipes, or human intervention. Moving on to section 3, proof in real-world spaces, taking this stuff out of the lab. By outfitting high-touch surfaces like door handles in a busy hospital or handrails in a public building, we're actively turning potential disease vectors into neutralizing barriers. So every single time someone touches these objects, instead of picking up a dangerous pathogen, they're interacting with a surface that is literally dismantling those threats on the spot. And hey, these aren't just neat theories from a lab. When copper is introduced into actual messy clinical environments, the microbial burden just plummets. Sally Oaks Hospital in Birmingham, they saw a 90% germ reduction. Several U.S. intensive care units saw drops of over 80%. Long-term care facilities in France proved it prevents bacterial spread over a 3-year period. Across the board, introducing copper objects leaves you with about 80% less germ load on average compared to your standard plastics or steels. You can see this beautifully applied in public transit, too. Take the Milan-Lino Airport, for example. Their stair handrails and luggage trolleys are now equipped with a solid antimicrobial copper range. When you have millions of passengers moving through a space every day, deploying this kind of material is just a brilliant architectural strategy to stop infections in their tracks. All right, section 4, securing our drinking water, the macro shield. Now, let's zoom out. To protect entire populations, we have to rely on something called the multi-barrier approach. Basically, it's this massive, integrated system of procedures, processes, and tools, all working together to catch contaminants all the way from the source right to your kitchen tab. As outlined in Justice Dennis O'Connor's report on drinking water safety, this framework acts as a literal gauntlet for contaminants. It's got 5 relentless layers. First up, you protect the source water itself. Second, you run it through robust water treatments with redundant steps. Third, you push it through a secure supply network packed with disinfectant residuals. Fourth, you maintain rigorous monitoring programs at the source, the plant, and the tap. And finally, you have prepared emergency responses ready to go. So if a threat somehow slips past one barrier, the next one is right there waiting to catch it. And we can't stress this enough, that redundancy is absolutely crucial. The tragic Walkerton outbreak in Ontario is a pretty dark reminder of exactly what happens when this carefully engineered system breaks down. It demands constant, unwavering vigilance. We literally cannot afford to let these barriers drop, ever. Which brings us to our final part, Section 5, Designing a Safer Future, the synthesis of public health engineering. So what's the big takeaway from all this? It's that true public safety requires defense in depth. We have to passively protect the surfaces we touch with materials that neutralize threats, while at the same time actively filtering the resources we consume, like water, through incredibly stringent municipal barriers. It's the ultimate one-two punch for environmental safety. But here's the catch. If we're going to implement these copper defenses in our buildings, we really have to respect the material. Pure copper has the absolute highest efficacy, bar none. Alloys like brass and bronze work too, but they've got to pack at least 60 to 90% copper. Oh, and here's a fascinating and crucial point for all you designers out there. Natural oxidation, when the copper darkens and gets that cool patina over time, that does not reduce its germ-killing power. But if you apply artificial surface treatments or clear coats just to keep it shiny, you will completely destroy its ability to neutralize germs. So, let it age. I love this quote here, which really hits the nail on the head. The ultimate goal of all these engineered systems is to let us just live our lives with an invisible but absolute peace of mind. When our airports, our hospitals, and our municipal water networks are actively engineered to fight pathogens for us, we can navigate the world with so much more confidence and safety. So as we look around our cities today, you really have to ask yourself, what other invisible design choices could we be making right now to stop the next great public health threat? By choosing the right materials and enforcing redundant, layered frameworks, we can literally engineer safety right into the fabric of our spaces. Thanks for joining me for this explainer. I'm willing to bet you might never look at a simple door handle or even a glass of tap water the exact same way again.